Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalua and I've been walking you through the physics class. Today let's quickly consider wave-particle paradox. That's a wave, particle, and paradox. Interesting topic. All right, we'll look at the wave nature of matter, then we'll consider the particle nature of matter, then we'll come to wave-particle duality, and we'll finalize the matter with the Heisenberg's uncertainty principle. The Heisenberg's uncertainty principle. All right. We've been discussing the matter of light and sound and other forms of energy, and in fact, to a very great extent, we've been discussing the issues concerning the electromagnetic radiations, electromagnetic waves, and we've observed many things about them. Right now, we want to consider, we've noticed that in all those things we've considered about them, we've observed that there were times we considered electromagnetic radiations or waves as waves, and there were also other times that we described them as though they were particles. So what's that all about? Let's clarify. What are they precisely? Are they waves? Are they particles? Are they both? Are they none? That's what this topic is all about. The paradox of wave-particle interrelationship. So how do we know something is a wave? Well, let's start with waves, the wave nature of matter. When we talk about the wave nature of matter, and considering the electromagnetic waves, rather, yes, electromagnetic waves, I would like us to start with focusing on light, because light can be easily monitored. At least we can see light with our eyes. So when we come to talk about the wave function of electromagnetic distance, so observe that we have energy being calculated with a relation to something that is related to waves, and we see HF or HV over lambda. So we see we have lambda. Lambda is absolutely related to waves, perfectly related to waves. And we see light. Light moves on a straight path. It obeys all the laws that waves obey. It can be reflected, it can be diffracted, it can be refracted, it can be transmitted, it can be, think about it, all the things that waves respond to, light responds perfectly. So that makes us to consider light as a wave. Of course, what is a wave? A wave is any disturbance that brings about the transmission of electricity through a medium without permanently displacing the medium. So it does not displace the medium completely. For example, I take my torchlight and I flash it through a glass. The light passes through the glass and it goes out of the back of the glass and it continues in its path without moving the glass towards the left or towards the right or pushing the glass forward or backward. That is wave. Just like our radio waves, at the transmission station, they are transferring the waves from the radio station, they are transmitting the waves, and we are in our houses, we tune into our radio to their radio station, and we can hear what they are saying, what they are sending to us all the way. I stand here in Nigeria, I pick up my phone, and I call a friend who is in Yugoslavia, and we're speaking. All because of waves are in motion. So we see waves. None of these things bring about a distortion, a permanent distortion in the medium through which they are being transmitted. We just see it go and come. So that's the wave nature of matter. But before we go further into this topic, in a few seconds, some questions will be displayed on your screen. We want to see how much you've understood what we have discussed so far. Please answer them, and I'll be with you in a few. Welcome back. So we've considered the wave nature of matter, and of course, when we talk about matter right now, we're using light as an example. So we spoke about the wave nature, that it can do everything that waves are expected to do. it can be transmitted, it can be reflected, it can be diffracted, it can be resonated, it can even be interfered. So what aspects in what perspective are we going to claim that light is a particle? That sounds odd, I know, but that's what we're trying to see. Is it possible for light to be a particle? Of course, yes, it's possible for light to be a particle. Evidences. What evidences do we have to prove that light is a particle? Well, we all know what is called the solar panel. Our solar panels or our photovoltaic batteries, they are exposed to sunlight and they receive charges. And also we describe the light coming from the sun, that is the energy tablets, that is tablets of energy, the things that bring the energy from the sun. We describe them as photons, and photons is a way of us describing light electrons, that is electrons of light. And we all know that electrons are particles. Electrons are particles. They are not just rays, they are not just radiations, they are not just waves. No, they are particles. So we can describe photons as particles. And if we are describing photons as particles, this is the function that declares light. It's what we are using to describe light. It's what we are using to identify with light. So we can therefore say that light also exists in a particulate form. We can describe light also as a particle. Of course, when we look at it, when we want to do our calculations for amount of electricity being generated in a photon, we always consider the kinetic energy, that is half mv squared. Of course, it is only a particle that can possess an m. It's only a particle that can possess an m, because if it is not a particle, it shouldn't have any mass. And of course, we see the velocity come into play there. So it is because of the mass it contains, then we can describe it as a particle. Of course, light is matter. I know many of us wouldn't have believed this before today, that light is a matter. Yes, light is matter. So in that sense, we come to the conclusion that light shares a duality, which is known as the wave-particle duality. It is possible for something to exist in two different natures. It can exist as both a wave, which actually does not distort, the medium through which it passes, and can also be a particle, which possesses mass and can bring about change in situations of things. Also, let's consider as part of description of light as a particle. Let's consider the Compton's effect. In the process of trying to displace electrons, the Compton's effect, C-O-M-P-O-N, Compton. The Compton's effect. In the process of trying to, in the Compton's effect, what he was saying was simply this: if there is actually a stationary electron on the surface of a metal, and a photon strikes that electron, he was trying to explain how it is possible for us to use light to radiate electrons or cause about the emission of an electron from the surface of a metal. So when light is being shone on that particular electron, the light, if it is powerful enough, it can give the electron energy, and the electron will move with a momentum, as well as the photon, which is coming also, will move off with another momentum. So you actually see the two of them moving probably separate ways. Of course, the momentum will equal to the original momentum of the entire setup. That is, the initial will be equal to the final. But you see that it is actually sending them in separate parts to further affirm that light exists in the particulate form. So that is what the light the wave particle duality explains, that matter can exist both as a wave and as a particle at the same time. Okay, let's discuss the Heisenberg's uncertainty principle. The Heisenberg's uncertainty principle. The Heisenberg's uncertainty principle simply says that the moment and the the moment and the position of an object which is being displaced cannot be calculated simultaneously. The moment and the position of an object which is being displaced, of an electron which is being displaced, cannot be calculated simultaneously. In other words, we have to calculate one and know the other, or we simply do not calculate any of them. A given expression that says change in energy multiplied by change in time equals to Planck constant, is greater than or equal to Planck constant divided by 2 pi. So we are not sure of exactly what it will be, but we know it will be about this. That's what the Heisenberg's uncertainty principle suggests. It's simply telling us that we may know everything, we may know a lot of things, but what we don't know is exactly. You cannot find out the exact thing. It is one of the reasons why today till date we still cannot tell what volume of rain would fall. We only say there will be showers, light showers. We cannot tell you there will be 100 centimeters of rainfall in Lagos Island, or 20 centimeters volume of rainfall in Ibadan. We can only tell, in fact, we cannot even tell the exact location in which this rain would fall. We can give an approximate location, saying, okay, it won't fall all over Lagos, it will fall in Ikoyi VI axis, but we cannot say it will fall exactly in this street to this street. This is due to the Heisenberg's principle. We cannot tell the exact position, and we cannot tell the exact momentum at any given point in time. So if we had been able to come up with something that can tell us the exact position and exact momentum, and we can calculate both of them simultaneously, then we would be able to move even further in our experiments, in our research. Okay, in this lesson we looked at the wave-particle paradox, and we were able to unveil the paradox. We talked about the wave nature of matter. Considering light, we say light is a wave. When we have our proofs that light is a wave, it behaves exactly like a wave. It can be refracted, it can be diffracted, it can be reflected, it can be interfered, and lots more. We also talked about the particulate state of matter, that is, particle nature of matter, and we also discussed that light also is a particle, especially using the Compton's effect to explain. In the Compton effect, we discovered that if a photon should strike an electron on the surface of a metal, it will displace the electron, and the electron itself will move in an opposite direction. So it is simply cancelling the wave nature of matter, which says it will pass through a medium without permanent displacement of the medium. So it actually displaces. So that is another thing. So that makes us to come to a conclusion that light can exist both as a wave and as a particle. And of course, the Heisenberg's uncertainty principle talks about the fact that we cannot measure and tell the momentum of a body, of anything, of molecules or atoms or electrons at every point in time, alongside with the position in which they would be. It simply says you cannot calculate both the momentum and the position of electrons in nature simultaneously. So I haven't spoken of all these things, I haven't learned about all these things. Some questions will be displayed on your screen. Please answer them. And if there is any part of this lesson which you didn't get clearly, you can go over the video one more time for better clarity. Thank you.